We know what they are, but we don't know now how they came to be.
Bathed in a perpetual glow, the rings seem to overshadow the planet. But with each encounter, Saturn itself grows more intriguing. Cold and distant from the sun, its clouds are obscure. Winds blow 3 times faster than on Jupiter. A turbulent ball of primordial gas, Saturn resembles a miniature solar system. Of its 18 moons, 4 were seen for the first time by Voyager. Composed of rock and ice, they're made of the stuff of comets. Most, like Tethys, are littered with craters. An impact on Mimas nearly blew it apart. Rhea and Dione are only partly cratered. Perhaps they were resurfaced by ice melted by internal heat. But none is more alluring than Titan, the only moon with a dense atmosphere. Voyager confirmed that Titan is steeped in organic material, the precursors of life. Astronomer Carl Sagan hoped the pictures would tell the story.
Voyager 1 was dedicated to make a very close flyby of Titan, the fabulously interesting big moon of Saturn. But to do that, we had to lose the option of Voyager 1 getting to Uranus and Neptune. And what I was hoping for was that the clouds that surround Titan might have breaks in them. And if we got very close, high-resolution camera might be able to see through the breaks and see what the surface of Titan was like. Fabulously interesting world because organic matter is falling from the skies like manna from heaven, and it certainly seems today that it has a great deal to teach us about the events that led to the origin of life on Earth 4 billion years ago. But as it turned out, there were no breaks in the clouds. We took hundreds of high-resolution pictures that had nothing in them, no detail whatever. Every world was a surprise. Not a one of them conformed closely to our vague expectations.
In 1980, its mission accomplished, Voyager 1 leaves Saturn to head for the stars. With the success of the encounter, a decision is made. Voyager 2 will go to Uranus. Ahead of Voyager lay a daunting 5-year journey. Uranus is twice as far from Earth as Saturn. Communication with the spacecraft will now be a challenge. Radio signals must travel across 1 billion more miles of space. Nothing could be done to strengthen the signal from Voyager. Its reception on Earth had to be improved. Dick Laser was project manager during the upgrading of the communication system.
Good day, John.
Hello, Dick. Good. Welcome back to the Mars site.
Thanks. Good to see you again. Hey, what I'd like to do today is take a look at the new X-band transmitter.
In California's Mojave Desert is JPL's Goldstone Deep Space Communication Center, one of 3 tracking stations located around the world.
The spacecraft itself, and in fact even our ground system on the ground, wasn't prepared to handle a spacecraft that would be as far away from the Earth as Voyager 2 would be when it encountered Uranus. And so we embarked on a plan to overcome the effects of distance. Okay.
We're
so
up
here
on
we are.
this surface now, and then we'll be looking into the cone and some of our electronics that we have.
Until now, each antenna has been sensitive enough to receive Voyager's transmission.
Oops.
But finding a radio signal from Uranus will be like looking for a needle in a cosmic haystack. Like a car radio, the further it gets from a station, the weaker the signal. For Dick Laser, the feeble transmission from Voyager would compound the problem.
The data transmitted from the spacecraft is transmitted through a radio receiver, but not with thousands of watts like your radio or television station, but the transmitted power is just a few watts, less power than the dim little porch light you may have sitting out in front of your house. And when it's received at the stations on the ground, the received power is on the order of about 1/20 the amount of power required to power my digital watch.
JPL's engineers would find an innovative solution.
A technique called arraying was devised, where in fact, rather than making the ear bigger, the antenna bigger, several antennas were electronically connected together so that in fact the effective hearing or listening area would be larger, and that was called arraying. At Uranus, we arrayed together 4 antennas down in Australia, 3 antennas here at Goldstone. At the Neptune encounter, the array here in the United States was truly massive because we arrayed together the 27 antenna array down at in New Mexico, the very large array VLA.
To overcome the low amount of sunlight at Uranus and Neptune, the spacecraft itself would have to be re-engineered. Its computers reprogrammed, JPL's foresight a decade earlier would now pay off. Edward Stone recalls.
Extending Voyager's reach beyond Saturn was a real challenge because we were going to extend the operation of the spacecraft 3 times further from the sun than had originally been designed for, out to where the sunlight was only 1/9 as intense as at Saturn, and where the signal coming back to Earth was only 1/9 as strong. So we had to make a number of changes. For instance, we had put on the spacecraft a special coding device called a Reed-Solomon coder, which today is in everybody's CD player, but at that time was a very innovative coding system. We had never turned that coding system on until after Saturn. We needed it because in order to go on to Uranus and Neptune, we needed a more efficient way to code the data coming back to Earth. We also had to learn how to stabilize the spacecraft so that we could take longer exposures and not have smear. And so we developed a number of techniques on the spacecraft to make the images more stable as we had to have longer and longer exposures in the more distant reaches of the solar system.
In January 1986, 8 years after launch, Voyager approaches Uranus. On Earth, the modifications have been successful. The signal from Voyager is loud and clear. Radio emissions from Uranus confirm the presence of a magnetic field, but it's unlike anything the scientists expected.
Planetary magnetic fields are generated by the flow of electrically conducting material deep inside the planet. In the case of the Earth, it has to do with the molten interior of the Earth, which generates our magnetic field. Now on Earth, Jupiter, Saturn, even Mercury, the poles of the magnetic field are very near the rotational pole of the planet because presumably the currents tend to be associated or formed by the rotation of the planet. We had a major surprise at Uranus where we found the magnetic poles were down near the equator of the planet.
Uranus is tipped on its side. The magnetic poles are tilted 60 degrees away from its rotational axis. A planet's rotation electrically charges its hot fluid core, generating a magnetic field. But at Uranus, the magnetic field is offset from its center. Because of these odd alignments, the solar wind sends the planet's magnetic tail spiraling through space like a gigantic corkscrew. At JPL, excitement runs high as the first images begin to appear. But an atmospheric haze obscures the view. Still, Uranus radiates large amounts of ultraviolet light, a phenomenon JPL dubbed dayglow. As Voyager skims over the equator, attention turns to the 5 major moons. Most are small and cold, like Oberon and Umbriel, ancient worlds of rock and ice pummeled by cosmic debris. On Ariel and Titania, the dominant features are global faults and cracks. But on Miranda, the bizarre is commonplace. Here, almost every exotic terrain Voyager has seen is jumbled into one.